Fortunate with the tentative interest of the students here. Just to have a quick, some of you might be here because you had nothing better to do this afternoon, like let's go see. Which of you may not follow the course later on? Okay, that's a very large number. I will ask for another room, but you know the system here. If we get one, obviously that will work. Bring it in and put it even there, that's fine. And then grab a chair. And we'll see what happens. So this is, for those who are not sure, advanced design and optimization of composite structures. My name is Christos Kassapoglou. Accent on the second A, Kassapoglou. Just, you know, if it took me years to learn my name when I was growing up, I expect you guys to learn my name now that you are older than I was, 5, 6 years old, trying to pronounce this. And please, I have a sheet here where I would like everybody to sign up: name, student ID, email, and then whether you've had composites before or not. The email is just in case there's an urgent announcement of something, usually something related to the homework or the final project. And it's easier if I send it to an email that you guys will check more often than others. Otherwise, I use the one on Blackboard. So feel free to do it whichever way you want, or even not even give an email if you don't want to. And I think this course is also, it's going to be online also for some distant learners. So hopefully it will be better as we go on and they will enjoy it also. The story is that you are an engineer, a young engineer, and your supervisor shows up and says, guess what? These keel beams that are on either side of the opening for the landing gear, which let's say are made out of some metal, will have to be redesigned because the requirements changed. Now you have to account, in addition to the usual loads, for a 9G forward crash, which actually happens to be the requirement for a fuselage crash requirement for composite structures. So you are supposed to design this, and you're supposed to design it like in a few days, as it's usually the case in industry. So hopefully by the end of this course, you will tell me how that's done, and we'll find out about it. So keep that in the back of your mind. This is a 4 ECTS course. Expect 4 ECTS worth of work. For those of you who know me, I intend to put everybody to full use because I think I benefit from your work also. I find out things that I didn't know about all these structures. The grade is based on 2 things: homework and final project. The homework is 4 problem sets, which each accounts for 12.5%. So the total from the homework is 50% of the grade. There's a final project, which accounts for another 50% of the grade. In some of the problems, there are no single answers. And so I'm looking for your kind of thinking. And if your answer is better than mine, you get a bonus. In particular, in the final project. Now, the homework will be usually due about a week after it is posted. Maybe a little longer, depending on whether we have covered the material sufficiently and whether the homework itself is doable in a week or not. There are no late homeworks in principle. You can try to negotiate, and my answer is no. I'm like an insurance company when you go for a claim. The first answer is no, because most of the people will then give up. If, however, you do have a legitimate reason and you give me in advance enough notice, then we may be able to negotiate something. Otherwise, there are no late homeworks. If you are 1 hour late, then the maximum you can get is a 9 out of 10. If you are 16 hours late, the maximum grade is 8, and if you are later than that, the maximum grade is 0. The final project will be due 3 to 4 weeks after it is posted, and again, that might vary a little bit, and there are no late final projects. If you're late, then the same kind of reasoning or the same kind of system holds as for the homework. I strongly encourage you to collaborate, but I do not encourage you to copy or cheat. Collaborating means you exchange ideas, you discuss it as much as you like. You even see the answers from everybody else that's willing to share the answers, but what you give me as a homework or a final project, it's your own write-up in your own words, and if I do see similarities that are beyond the acceptable level, then I get very upset. So please make sure, whichever way you choose to collaborate, you provide it in your own words, or you disguise it enough so that I cannot tell that you're copying, but it's going to be a challenge for both sides. Now, the final project is sizable in terms of duration and amount of work. That's why it counts for 50% of the grade. And that's why I, again, also urge you to work in teams. That means you can form a team, no more than 4 people per team, and you can work on it all together. In the end, you will submit, each of you, one report separately. So again, each person will have to write down exactly what the whole team came up with in their own words. And you cannot submit one report for 4 people. I want to know the differences between the different people, and on the front page of that final report, you will also give me the names of other team members that participated in your effort. You can also do it alone. People have done it alone before, and in fact have done quite well, so it's your choice. As we approach the final project, if there are people who would like to be on a team and have not managed to find a team yet, then we will try to find teams for them, which is an interesting situation as I try to twist people's arms to accept other people in their teams, but we'll figure something out on that also. It's been working reasonably well for the last 5 years. Okay, now, any questions so far related to the homework and final projects and anything you've seen so far? Okay, good. You're supposed to know reasonably well everything that's shown at the second half of this slide. You're supposed to know basic structural mechanics and strength analysis. You're supposed to know composites, classical laminated plate theory. That's why this is called advanced design and optimization and not just introduction to composites. So if you know it, great. If you don't, we will cover it in the next 2 lectures. So the equivalent of 10 lectures will be covered in 2, just to suggest to everybody where we are supposed to be in terms of common knowledge. There are references you can use and background and a whole bunch of other things that hopefully will help you. People have done it before, working in this course without any prior knowledge in composites. Half of them give up and half of them actually manage to do it, and quite well. It's a significant amount of work. It's your choice, and I'll help you as much as I can. You're supposed to know your basic math, calculus, ordinary differential equations, infinite series. We'll do lots of them. And of course, a little bit on structural design and optimization. Those who have seen me before in second year structures, you know, there will be more of it, but much more intense now. So you've seen some of the way of thinking related to metal structures. Now we'll be doing much more of it for composites. It would be nice to have access to a software that calculates the ABD matrices. It will become clearer later on for those who don't know what those ABD matrices are, and that does first ply failure. If you don't have access, we will provide you with access. I strongly recommend to write your own code, whether it's just for this course or if you intend to take the follow-on course later on. You will need a code that you have written and you know what it does, and you can trust it for calculating stiffnesses, the ABD matrices, and for calculating first ply failure. So at some point, in fact, homework number 1, you'll have to do that. You can't answer homework number 1 without having access to this. I will give you access also, but I'm also suggesting to you that it's to your advantage if you write it on your own. Now, why do I have this? Because I'm going the wrong way? No. Yeah, okay, the material covered. In 2 lectures, we'll do the classical laminated plate theory or classical lamination theory, and we'll talk about first ply failure criteria, which is what starts failing in a composite laminate. Then we'll cover structural design requirements, talk about composite plates, buckling and post-buckling. Then we'll talk about stiffeners, beams, and so on. You will notice these appear to be out of sequence. First we will do plates, then we will do stiffeners, but the reason for that is that we can do some of the stiffener cases the so-called crippling failure of stiffeners. We can do it as a special case of plate buckling, so it's better to start with plates, then we do stiffeners, then we put the two together and we come up with stiffened panels, which is one of the major structural elements in a fuselage or a wing or other flying contraption. And then, of course, we will have a comparison with the counterpart of the stiffened structure, which is the sandwich structure. We will close with design guidelines for producibility and robust performance. Basically, there's one thing to have analysis and another thing to be trying to be prepared for all kinds of contingencies in the design. So robust means what happens if something goes wrong. Is your structure going to collapse completely, or does it have enough extra margin of safety or enough ability to redistribute the load as it locally fails? So these become important, and we'll mention some of those in closing the course. And every once in a while it will be fairly obvious that the composites, if you changed certain properties, will become metals, and the same approach holds for metals also. Lecture material will be posted on the Blackboard no later than the day of the lecture. This lecture was posted yesterday. Usually I try to post it the night before. I cannot do it earlier than that because like most people, I'm not smart enough to not prepare for the lecture. I have to look at it the night before, and that makes me change some things in view of what may have been discussed in previous lectures. So as a result, the earliest that the lectures will be posted is the night before or the day before. Any questions on this? Okay. There is a textbook which you may use if you want to. Second edition of this book. If you don't want to use it, that's fine. The lectures presumably cover 90% of the material. The book covers significantly more. There's a little bit of a complementary situation here. Some material in the book is not covered in the lectures. Some material in the lectures will not be covered in the book. So it's your choice. If you want to use it, you can get it at lower cost through the VSV. Any questions so far on this? Because now we are switching to real material. Okay, so let me try to go through a history of composites, advanced composites. We are not talking about wood or other types of composite materials, especially as that history applies, has been manifested through applications in civilian aircraft. It was in the 1950-something where some Germans at the University of Stuttgart were approached or were for the first time exposed to this material called fiberglass. Usually what happens is some manufacturer of material will come to you and will tell you, I have this new miracle material. It has happened to me a couple of times when I was in industry. And they are absolutely convinced that this material just blows everybody out of the sky. For example, when aramid came out, everybody was checking it in tension, and they found phenomenal properties in tension. So people started getting very excited, not just the manufacturers of aramid, but also the whole industry. Turned out in compression, it's the worst thing you can ever imagine. And it also turns out most aircraft structures or aerospace structures are mostly in compression. They are not as much in tension, or tension somehow you can figure out. Compression is a nightmare. So they were approached about this fiberglass, which was used on boats or was starting to be extensively used on boats, and they were designing sailplanes. In fact, 2 professors and 6 students were involved in a project to design this Akaflig Phoenix sailplane, and to their credit, they decided to use a new material. And in fact, it worked extremely well. They came up with this sailplane that worked very well. I think all in all, they made either 12, I think they made 12 of those. And imagine these are students now producing sailplanes using a new material. So that was the first introduction, serious introduction of composite materials in something civilian that lives off the ground for a significant amount of time. In the 60s, the helicopter industry started realizing that there is something to these new materials, composite materials. A helicopter is pretty much a very ugly contraption. If you look at the shapes, there's nothing to brag home about. And in fact, it's the aerodynamicist's nightmare to try to keep the drag in any kind of a reasonable value, but they do work. And they have actually some extremely challenging problems. The blades in a helicopter can be approximated as beams. So what is simpler than beam theory? Well, first of all, it's very large deflections. It's not just our standard Bernoulli-Euler beam. Second of all, it's very large rotations. If you put a camera at the root of a blade and you see what happens to the blade as it rotates, it's exactly like macaroni. You won't believe how much it flaps and rotates and twists. And as if this were not enough, in order to keep its dynamic performance within the range that you want, you have to have certain frequency response. And that means that as you start from the root of the blade and you move towards the tip, you have every 1 centimeter or every 5 centimeters, depending on how accurate you want to be, a different value for the bending stiffness, EI, Young's modulus times moment of inertia, and for the torsional stiffness, GJ. So you have to come up with a structure which has continuously varying EI and GJ, does not break, can do large deflections and large rotations, and can deliver the aerodynamic performance you want. So in fact, helicopters barely work. If you look at it as an optimization problem, the constraints themselves pretty much move you outside the design space. There are solutions, and turns out they sort of look like this. So the French were among the first to recognize that if I have these blades, which have this huge centrifugal load on them, a tensile load, but they bend and rotate like crazy, as I try to make them bigger, either in length or in chord, it's impossible to do that with a metal structure. It becomes too heavy, and its frequency response is not what they want. So they were the first, or among the first, to switch to composites. And now there is no helicopter out there that's worth its name as a helicopter that doesn't have composite blades. It's the only way you can achieve the performance required. So despite their appearance, helicopters have extremely challenging problems. And anyone that's really in for difficult problems, I would recommend they look at this kind of application of simple beams that are not very simple once you get into them. In the 70s, a gentleman by the name Bert Rutan, a very well-known aerodynamicist and airplane designer, well known because he designed the flying gizmo that went around the Earth without landing, or he's now designing these flying gizmos that will go to space with Richard Branson, Virgin Galactic, and so on. So it's actually a person who has been involved in very challenging problems with various degrees of success. In the 70s, he recognized that this material, again, these composite materials, would give certain advantages. They could give you pure laminar flow, because if you make the whole structure without any rivets, and you can maintain the aerodynamic shapes you want, which you can with composite with the use of proper molds, you can actually get laminar flow, your drag goes way down. And he also recognized that you can generate shapes that, such as canard shapes and so on, that will give you some extra performance in certain windows of the performance envelope. So he designed a series of canard little airplanes, 2-passenger or 4-passenger, I think was the largest. But anyway, it's the very easy and the long easy, which were extremely successful. So at this point, the real manufacturers of airplanes started getting excited. There's this material that's been tried for the last 15, 20 years. And of course, they knew of what was going on in the military side. The military grabbed these materials very early, but they wouldn't tell anybody what they were doing. So it's one of those situations where in parallel the civilian sector and the military sector had to try to move along. And they said, okay, maybe we should start making bigger airplanes. So here comes now one of the major characters, Bill Lear. If anybody is interested in a major personality in all aspects of the word, tremendous engineer and fantastic, brilliant person, you should read up a little bit on Bill Lear. He's a classic case of U.S. History, dream kind of history. In high school, early in high school, so that would be when he was about 16, the oldest, maybe, or maybe 15. He was giving a hard time to his professors. He disagreed with just about everything they said, to the point that they got extremely upset, and they threatened him to kick him out of the high school if he continued his behavior. So he chose to leave high school on his own because he wasn't going to relax on criticizing all his professors. So without finishing high school, he left, and he decided to enlist in the Navy, but because he was underage, he had to lie about his age, and eventually they accepted him in the Navy, where he started working on the airplanes of the Navy, and he became quite a good mechanic because he was a natural in that kind of stuff. And in fact, one of his strongest points was electronics. He actually was a wizard in electronics, and he came up with a radio that you could use in a car, and it would work isolated from feedback from anything else, and it would give you beautiful performance with nice speakers and everything else. So he decided that there was no good radio for cars at the time. He decided that this was a good thing that he should try to market. It so happened that in Detroit, as there is every year, there was a huge auto show where all the big automobile producers would be there and all the prospective big buyers would go there. So he wanted to go there, but he had no money because he had to pay an entrance fee in order to participate and have a booth. So he set up on the parking lot outside this huge five-star hotel, and he had a car, his own car, in which he had installed this radio. And he was playing that radio, and before you know it, people, instead of going into the hotel for the big show of the automobiles, were going and talking to him about this wonderful radio contraption. And in fact, he got so many orders that he was able to start his own company, a very well-known company today by the name of Motorola. In addition to that, once he realized how good he was, obviously there was no limit for him, and then he looked into control systems for airplanes, and I believe he was the first one to set up a reliable control system for multi-engine airplanes. And there are some funny stories related to that. He used to try everything on his own. So he had his own airplane, and he had set up the control system where he was checking something in the control system. And in the airplane he had his son, 12-year-old or 10-year-old son, and his wife. And as he was fooling around with the control system that he was setting up, he didn't realize that the airplane was drifting away. You know, autopilot at the time was not the best autopilot you can imagine. In fact, he actually improved the autopilots of the time. And he ended up in restricted Air Force space, you know, like Area 51. It's not necessarily Area 51, but it was clearly restricted Air Force space. And before you know it, a couple of Air Force airplanes are, you know, coming towards him. And he was smart enough to realize that they were coming for him. So he tells his son, you sit at the controls, and he and his wife hide. So these two big airplanes approach, and this little guy is trying to, or pretending to be flying this airplane. So obviously they said, you know, the kid doesn't know what it's doing, and they sort of let him go without too much harm. So he then decided that if we want to make a airplane of quite some performance with about 10 to 15 passengers, the materials would be composite materials, and the design would be a good design. In fact, in his mind, a pusher propeller would be the way to go. So he started the whole project, the Learfan. The Learfan is actually the first all-composite airplane that almost got certified. Getting certified is actually one of the biggest challenges. Anyone can build an airplane, but not anyone can get it certified. And if you see how much money the big companies or small companies spend in order to convince the certifying agencies that the airplane is safe enough to be allowed to fly, you will realize how challenging and how difficult that is. So it almost got certified. The only reason it did not get certified had nothing to do with the structure itself. It was a problem with the transmission system, because he had one propeller and two engines. The transmission system, as far as the certifying agency, the FAA, was concerned, should have a certain backup to a second system just in case the first one failed. And at that time they had used all the money, and actually he had just passed away, so they couldn't get it certified just for that. But the composite structure actually was very, very good, and it had been given approval to fly. The whole airplane was in fact so good that when they started flight testing, when you start flight testing, you need a chase plane. You need another airplane that will follow you very close and will see if something goes wrong, flaps, ailerons, and so on, and help with telemetry and radioing back and forth between the pilot and the base and so on. So they invited some person who was a professional owner of chase planes, and they said, we have this airplane, it's a pusher propeller, and we will need a jet. And he said, you must be kidding, the jet is too fast. You know, I will come in with the turboprop and it will be fine. So I think Bill Lear himself said, okay, we make a deal. If you can keep up with my plane, fine, you use the turboprop, we pay you. But if you cannot, you bring a jet and we don't pay you. And stupidly he agreed. So his turboprop could not keep up with this, and he had to bring in a jet to do the chasing for free. So this was in the early 80s. And a bunch of engineers, when the company went down, moved from Reno, Nevada, essentially, to Wichita, Kansas. If you've never been to Wichita, there's no reason to go there. It is not the end of the world, but you can see it from there. I speak from experience, having lived there for 3 years. 3 of the best years of my life, but still, you can see the end of the world from there. Those guys and Beech Aircraft, which was a company making small airplanes, but much bigger than these ones, they had decided to move to the next big product that would really corner the market, and they were looking for a great airplane designer. And if you look at the similarity between these two, it's obvious who the airplane designer was. Bert Rutan was hired to design the Starship One. All composite, and when I say all composite, I mean all composite, other than the engine, everything in there. Oh, and the seats, the metal part of the seats. Everything else was composite. I mean, we went overboard on that project. Canard, because that's what Bert Rutan will tell you is the best way to go. Presumably a laminar flow over this big wing and the winglets for your, what's it called, yaw control. So we started working on this, or they started working on this, and I must say this is an engineer's dream. You have 200 people in this huge room because there are no individual offices. All the groups work together, the manufacturing guys, the materials guys, the stress engineers, the dynamics, aerodynamicists, and everybody else. And you work on this because you like it. Basically, it was typical on a Friday they would say, we are testing tomorrow. To test tomorrow, we need to solve this and this problem. And some of you must stay here, and they may have to stay throughout the weekend. And people would actually volunteer, including myself. And all we had to do is call our friends or girlfriends or boyfriends and tell them we won't be home for 1 or 2 days, and we would stay there overnight trying to get this thing to work. And despite the aerodynamic design, which was not good enough, it turned out, we made it work. We, the entire group, I was only one of many. This was the first airplane to get certified in the late 80s, the first all-composite airplane. It was not a success in the market because it fell short of its projected targets in terms of performance, range, and speed. And that has a lot to do with the aerodynamics, increased drag, and a few other problems. For example, if you have a very relatively long beam and you decide to hang at its tip a mass, those of you who remember the dynamics, you realize that it doesn't help very much on your frequency response. And in fact, to hold this winglet onto the wing, you will need what's called a fitting, a three-dimensional structure that will hold the two together. And because it's the tip of the wing, you have to have a lot of supporting structure. It ended up being a titanium fitting bigger than my hands can go around it. So that's a lot of mass hanging at the tip there. So your dynamic performance is also suffering from this kind of stuff. But overall, from the structures perspective, from understanding the new materials and actually paving the way and saying, okay, this is a challenge that anyone can take if you have the right people to work on it, it was actually a success. So bigger companies then decided to really jump into this bandwagon. In fact, the 737 horizontal stabilizer had already been made by, or was being made and certified at about the same period with a sandwich composite structure. And the biggest contributor, or the biggest risk taker, if you want to call it, in the early days was Airbus. They decided to go beyond where everybody else had been before. And the A320 had significant amount of composites, the vertical tail and the horizontal. And in fact, the design had a lot of innovation in terms of manufacturing. They were the first to actively pursue the possibility of modular structure, where you make a big structure out of identical or nearly identical smaller pieces. That drives your cost way down. And if you have a good method to do all this assembly in an automated fashion so that it's accurate and fast, then you actually get a very good structure. Then for 10,000 reasons, they abandoned that approach, and only to start thinking about it now. But the bigger companies now are starting to use composites. And it was about early 90s to late 80s that there was a very interesting study that Boeing and Airbus put out separately. They wouldn't do it together. In fact, they do that every year or every few years. They come out with projections of what they think the market of the future will look like. And perhaps the most interesting time where they had very significant differences was around that time in the late 80s. Boeing said the future is for smaller airplanes that will use the hub and spoke idea, where you have a hub and you fly 2 hours, 3 hours at the most. Yes, we will need some bigger airplanes like the 747. As far as Boeing was concerned, that was sufficient. Airbus was completely different. They came out and said the future is the bigger the better. And in fact, that was the root of the A380. So I think this is the beginning of what will become an interesting case study for management schools in the future. How the biggest players came up with completely different estimates, and how they each then either capitalized or not capitalized on those predictions. Because what happened? Airbus started advertising the A380, and everybody wanted an A380. Or at least they showed interest. And Boeing realized that nobody was interested in smaller airplanes for some reason. By nobody, I mean the airlines themselves. So Boeing came up and said, okay, we will make a stretch of the 747. But that stretch was not going to get even close to the as much as 800 or 750 passengers that the A380 could conceivably include. So that the airline said, we're not interested. Then Boeing said, okay, we will give you the transonic cruiser, which will go, instead of 0.85 Mach, we'll do 0.9, 0.95, will be faster. So it will save you half an hour to an hour from going to New York to Sydney. The airline said, big deal. In fact, they put in another word in between the big and the deal. We are not interested in that either. So Boeing is actually losing out. Orders are coming in for the A380, and Boeing doesn't seem to have an alternative. And this is where it gets interesting. Was it done on purpose, or was it not done on purpose? What is about to follow. The Boeing engineers had been working on composite airplanes since 1991. And they had made a lot of progress. There was a big program funded by NASA that a bunch of US companies, including the company I was working at the time, had participated. So a lot of the basic knowledge either was there or was being developed. So at some point there was one of those secret meetings. Some of you may know the story. Boeing had this secret room where you would go in one door, you would have to leave everything outside in terms of calculators and everything else. And they would discuss the models of the future. And some big vice presidents or other management dignitaries were present, and they asked the engineers, do you guys think that a composite airplane is possible? And they said, well, give us some time, give us some money. An engineer never admits anything unless he's already done it. If you haven't done it, then you come up with 10 reasons why something might go wrong, even though most likely it will not. Then they were asked, okay, do you think that if we used composites, we could save weight? Yes. How much? About 10 to 15%. So they did their calculations, and they said, okay, better engines, lower weight, improved performance with improved aerodynamics, 20% increase in efficiency. And before the stress guys and the composite engineers at Boeing knew it, a decision had been made, and they were told, you're starting now, the next airplane is going to be a small airplane compared to the A380, and it's all composite, which was a nightmare because these guys did not have so much pressure in their lives before. But with that now, they started approaching the airlines who had told them we couldn't care less about your ideas. And they said, I'm going to give you an airplane that's 20% more efficient and a whole bunch of other things. No corrosion, reduced maintenance costs. Of course, all these remain to be proved, but that's what they said. Then before they know it, they started getting all these orders left and right. It was actually the most successful launch in history, the 787, which is now flying. And if they could find good batteries that don't light up in the middle of a day or the night, then they would probably be a very successful airplane. So A380, with a bunch of composites, in fact, a lot of fiber metal laminates, which were discovered here, came out, but it's not doing too well in sales right now. In fact, if it hadn't been for the Emirates giving a huge order to Airbus last month, I think they would have been really ramping down production. 787 is still trying to ramp up. They have a lot of orders and they're still selling. And of course, what's not shown here is the A350, which is the competitor to the 787. Airbus is not a company that will just sit back and relax. In fact, when they saw the success of the 787, they changed completely their story about what's the airplane of the future. And they came up with a new design, an extremely good design, which is now flying, and they have been selling extremely well left and right. So the moral of the story is that you need a challenge that you can barely work with. You need a market that you can convince you know the answers even though you might not. And you need a bunch of people like you guys who are willing to spend much more than 8 hours a day, not paid necessarily, just because it's fun. And then you can get something like these guys. So over the years, if you look at the stories, and I included a couple of the military ones because it shows how much faster composite implementation was occurring in military airplanes. This is the F-14, F-15, F-18 jumps here. The AV-8B, or the Harrier as it's called, is more % composites. In fact, the entire cockpit is all composite. While, you know, B787, 767, A310, you know, they're struggling along until, of course, the 787 and the A350, which, well, the really big jumps. Of course, what's happening in the military side always helps what happens in the civilian side, because some people eventually work for the civilian sector, or some things leak or become declassified. I used to work with two guys that had been working on the B-2, the flying, what's it called, this fish like, you know, the black huge bomber, which is all composite. And I naively at the time would ask them, so how do you guys do this, you know, impact on composites? And they would always give me the exact same answer. I can neither confirm nor deny that I know anything about what you're asking me, because they've been clearly told during security clearance meetings that this is classified, and by classified we mean classified, so your only answer can be I can neither confirm nor deny. But things eventually leak one way or another, so there is eventually this benefit, and people can actually take off and use these for civilian applications. So this is our background, and we are about to start our review of classical laminated plate theory. Are there any questions on so far on history of composites as presented by me? It's not necessarily the correct version, it's one of the versions. All right, let's meet in 15 minutes. And for some reason, I'm convinced there's more than 15 people in this room. So any of you who haven't signed up and intend to... So what's wrong with you people? Like after the 15th person, you said, okay, screw the others, let's have this. So please pass it around again and complete the list. Okay, so classical laminated plate theory is the theory that was developed in the 60s, or was mostly developed in the 60s. And a lot of people, the people working at the Air Force Materials Laboratory, which was the center of the best research at the time for composites and for quite a few other things, were involved in this. It's basically one way of representing plates whose properties are not the same in different directions. So I'll be going quickly through this in the next 45 minutes. Airplane structures or any flying structures have at least one dimension that's very small compared to the others, like we have plates and shells that represent the fuselages and so on. So usually we have plane stress conditions, so under certain circumstances we may have plane strain, and then we can go into the three-dimensional, and for isotropic materials we have the isotropic elasticity. Now there are complete parallels to these for composites. The big difference is that this is an anisotropic elasticity, which complicates things quite a lot, especially when you try to solve problems in general. So two things are that we are interested in. One is the stiffness or the elastic response. If I apply a load, how much strain or how much deformation do I get? And the second thing is, if I apply a load, when does my structure fail? So as far as the first part, the so-called elastic response, if you have isotropic materials, then you only need two elastic constants, any two of these three. E, Young's modulus, G, the shear modulus, and nu, the Poisson's ratio. And as you well know, for isotropic materials, this is the relationship between the three of them, so any two are enough to define the others. Now, if I have anisotropic materials, then instead of two, I may need as many as 21 completely independent. Why are they 21? Because in general, I have 6 stresses and 6 strains. I'm going to use matrix notation just because it's a little easier. We have 6 stresses and 6 strains. So if I'm going to relate those, then I will have a 6 by 6 matrix here. Is there enough room? E13, E14, E15, E16. And it's a symmetric matrix. So if it's a 6 by 6, and you calculate the terms that are the same because of symmetry, then you are left with 21. Conceivably, above the diagonal, including the diagonal and everything else, there's 21 terms that they could be independent of each other. It so happens that most materials that we use don't have to fall into this category, which is very difficult to characterize, just a number of tests that you would need, for example, to get these 21 stiffness values would take forever. But it so happens that there's a class of materials, the so-called orthotropic materials, for which 4 elastic constants are more than enough. Basically, there's the stiffness, as called here EX, stiffness in a certain direction X. Then perpendicular to that, there will be a different stiffness EY. There's a shear modulus and a corresponding Poisson's ratio. So that's the stiffness story. Now for failure, in metals, everything starts with yielding, and that's very nice. Just about all metals will yield to some amount, and that's reasonably well understood. Basically, we have plastic deformations, and you can go from there in the post-yielding final failure collapse in a relatively well-defined situation where we understand what's going on in the material. In composites, because we have 2 components, that's why they are called composites, there's at least 2 components, the matrix and the fiber, we have a whole bunch of things that can happen, and there's even no guarantee what happens first and what happens next or how they interact. The matrix may yield. The matrix will eventually crack. You may have delamination, which is separation between layers. Remember, we are putting together different layers of this orthotropic material that we will call eventually a composite to make a laminate. So between the layers, we can have delamination. Those of you with me in the second part of the course in the fourth quarter will see a lot about delamination. We can crack or break the fibers, or we can crack or break the interface between fibers and matrix, which is completely different than the fiber and the matrix. So all these usually to some extent happen, and they interact, and it's a nightmare to find out what's going on. So composites are inherently much more complex. The irony is, because they are so complex, we tend to simplify them so much that they sometimes are even simpler than metals. But of course, this kind of simplification leads to approximations that are acceptable part of the time, but definitely not all the time. If you look at a composite and start from the basic constituent and start going up, you will see that down in the micron level, we have a single fiber, and on the surface of that single fiber, there may be some defects, some tiny cracks or scratches, or maybe even inside the fiber, but we can't see it most of the time. If I now go a little larger in scale and I look what happens on 3 different layers. Here we have 3 different layers. This one to the left of the white region or the white-gray region, this one is a minus 45 ply. We'll talk about directions and orientations much more later on. The one in the middle is 0. So essentially the fibers in the middle are running along the length of the photograph shown there. That's why it has completely different color. And then we have again minus 45 on the other side. Basically the little dots that you see are the actual fibers coming at us. So under some kind of loading you can crack the matrix. And when you crack the matrix, the crack goes in between the fibers at the beginning. You cannot break the fibers, they are much stronger, so if you're a crack and you're trying to move around, you will select the path of least resistance, which means you will zigzag a little bit. That's why it's not a perfect straight crack. And you hit an interface between the minus 45 in this case and the 0, or in this case the 0 and the minus 45 on the other side. And then as a crack you have to decide, do I stop or do I continue? And if you are a strong crack, then you will try to move into the 0, and sometimes you can do it. Otherwise, you will move along the interface. Basically, as soon as you reach, as a matrix crack reaches a layer or a ply with fibers in a completely different orientation to the fibers in the ply from which it was coming from, it now becomes extremely difficult to crack those fibers, and therefore you select to turn around. That means now the crack moves between the 2 layers and it becomes what's called a delamination. Now you can combine these excuse me, as you go to an even larger structure, and you will see now a whole bunch of delaminations in a composite plate which was about 1 centimeter thick under impact. This was impacted, and which is one of the major threats for composite structures. So you get these kinds of delaminations that are much more pronounced now, and many more of them through the thickness. And you also get, if the lighting permits, between the delaminations you can see there are actually cracked entire plies, which means that you also have some broken fibers. And finally you go one step beyond in the size. Now you are in the centimeter level, where this is actually the face sheet of a sandwich tested in compression, and you see how it failed, where you had this bulging out or small half wave of the face sheet pulling away from the core and breaking in compression. It's the so-called wrinkling failure. So there are different failures or different combinations of failures at different scales, and there's a big decision that one has to make. What level am I modeling these? If you are a person with infinite computer power and with physics background, you can start way down here or even smaller, talking about the molecular or even atomic level, and try to then go from that integrate up as you go in scales. I don't think there's enough computer power and knowledge even at this point to be able to start at such a lower level, even though eventually we have to start moving down in that level. Typically you back out and you say, I admit defeat. I will start with a building block that will be the layer itself or the ply, and I will characterize failure at that level, even though in reality there are all kinds of mechanisms that happen at even smaller levels. I will characterize it at that level, and based on what I know at that level, I will try to predict what happens at the full-scale level. And usually you fail miserably because it's not as simple, it's quite complicated and we don't understand much, and we'll talk about that, about failure criteria, but that's the best we can do today. So keep in mind that the problem itself is complex. The mathematics and the physics are very complex. The computational power can be quite prohibitive. Progress has been made in many respects, and we are understanding some of these failures better than before, but we have to make approximations. In fact, the whole course is about making approximations. So let me open a parenthesis here. I was going to go for an interview at a company in the US, and usually you try to find as much, if you're going to go for an interview, you better find as much as you can about the company, what they do. I mean, you're not just going there because they have a big name. You want to go there because they do interesting things. So I found out about some of the people that were working at that company, and one person that I knew said, you had better be prepared for some difficult questions. So like what? I said, no, I know my math and everything. Oh, the math is the last 5 hours. Don't worry about that. It's what is, which is true. The last 5 hours I was doing math. The first question they will ask you is what makes a good engineer? And if you answer that well, then it's going to be much easier. If you don't answer it well, you have to make up that problem. So anybody knows what makes a good engineer? So we might as well say it out loud, man.
Making the right assumptions.
Exactly. A good engineer can presumably in a piece of paper, in fact, this, the usual story is on napkins. You write, you scribble something and it's within 30% because you know which assumptions to make to simplify the real structure. So that's the whole course here. We'll be making a whole bunch of assumptions, some of which will be quite arbitrary because it's convenient, but many of them will be actually based on a realistic understanding of what the structure does. And your final project will have a lot to do with you guys making the right assumptions on your own. You can ask me anytime for homework or the final project. You can come to my office or during lecture or whatever. But after a while, I will be leaving it up to you to make the right assumptions. So the orthotropic materials are the ones that have two planes of symmetry. So if I make a section cut in a typical composite, in fact this is showing two layers, and I draw a vertical line here and a horizontal line there. Now, other than this relatively clearly well-defined resin layer, which is the resin layer between the two plies, it's very difficult for you to tell whether you are on the left or on the right-hand side, in the sense that there appears to be symmetry with respect to this vertical plane perpendicular to the page and this one, or the horizontal plane. So if there are these two axes of symmetry or planes of symmetry, then the analysis, the modeling simplified tremendously. Those 21 unknowns become only 4, the 21 stiffnesses. Of course, as you can even tell from this scale at which I have the picture, there is no such thing as perfect symmetry, and the smaller or the more you zoom into the structure as shown here at the bottom right, the more asymmetric it becomes. So depending on what level you are modeling, whether your symmetry holds or doesn't hold becomes a big deal. If you're trying to model the structure, and as I said, we select arbitrarily to go to the level of a ply. The ply is the one layer of fibers and matrix. And that's our starting point. You could go further down or zoom further in, but as I said, becomes computationally very expensive and very difficult to understand what we're doing. So we're going to start at a ply. And the ply consists from fibers and matrix. One example is where you have unidirectional fibers, so it's a unidirectional tape in this matrix that make this kind of a ply. And the approach, an ideal approach, would be I characterize the fibers, I know their properties, stiffness and strength. I characterize the matrix, I know its properties, stiffness and strength. I put them together, and if I know what I'm doing, I should be able to predict the properties, stiffness and strength of a ply. Turns out it's reasonably successful when it comes to stiffness. It's miserably failing when it comes to strength. There's certain things about the mechanisms of failure that are not easily understood on the basis of what causes a fiber to fail and what causes a matrix to fail individually. When you put them together, that interface and how they interact becomes a little difficult to understand. So you can say, okay, I have my micromechanics, which I can use when I'm comfortable with, but I recognize that that might be limited. And I can then say, okay, let me just take a single ply with the fibers in it and characterize that. By characterize, I mean let me do my stiffness and strength tests, and on the basis of that try now to build up an entire laminate and its own properties. And this is the level which we will be dealing with mostly in this course. So when I stack them together, I get what's called a laminate. So I can take plies or lamina, one lamina, plural laminae. There's the extent of my Latin. And we get a laminate. Now the laminate has three axes, of course, X, Y, Z. And it has forces and moments that we will be talking about some more in a little bit. But those forces and moments will cause deformations. The question for us is, if I know how a single ply behaves, how can I now determine how the stacked up set of plies or laminate will behave? As I was saying in the previous period that are shown there in the blackboard, in general, I have 6 stresses and 6 strains. And because we have selected an orthotropic material, some of these stiffnesses here are very conveniently 0. So in fact, the matrix shown in the blackboard for an orthotropic material becomes this, which is this 3 by 3 portion at the top left, and then only diagonal terms that relate shear stresses to shear strains. So this is the general situation for a single ply or layer that's orthotropic. Now, if you remember from your medals, the equivalent relationships for the 6 stresses and the 6 strains, epsilon x, epsilon y, epsilon z, and the shear strains shown here, gamma yz, gamma xz, and gamma xy. This is what happens for a metal, where everything is conveniently in terms of the Young's modulus and the Poisson's ratio. So the equivalent to this 6 by 6 matrix for a composite, where each term is in general independent of any other, is for metals what's shown here. Now, if the laminate, the stack up of plies, is thin enough, then we make our first biggest and most important assumption for the entire course, which we will actually revisit later on. The assumption that through the thickness there are no stresses. Basically, we say that I have a thin plate. At the top of this thin plate, I have 0 stresses because there is no stress applied. At the bottom of this plate, I have 0 stresses. Therefore, I can assume to a first order that through this thickness here, there is no variation in stresses. In stresses, out of plane stresses, sigma z, tau y z, and tau x z. So if they are 0 at one surface, they will be 0 everywhere else. If I can do that, then the relationships from the previous 2 slides here become significantly simplified, because I have a bunch of zeros for the sigma z, the third equation, tau yz, and tau xz for the fourth and fifth equation. And what that allows me is a couple of things. First of all, I can directly determine the shear strains in out-of-plane gamma yz, gamma xz are 0. So that takes care of those two equations. There is a single equation at the bottom that relates the in-plane shear stress to in-plane shear strain, which is just well-defined, nothing to worry about. And then I have three equations at the top, which are in terms of the three strains, epsilon x, epsilon y, and epsilon z. So what I can do now is I can eliminate epsilon z from the third equation here. And I will then be able to write my in-plane stresses, sigma x, sigma y, and tau xy, in terms of the in-plane strains, epsilon x, epsilon y, the two normal strains, and gamma xy, the shear strain. When I do the elimination and collecting terms, I will have a quantity multiplying epsilon x in the first equation, which we call qxx, and then a quantity multiplying epsilon y, which we call qxy, and so on, which means I can create a matrix relationship for the stresses as a function of strains in terms of these stiffness terms. So a single ply is characterized by this set of relationships as long as this holds, that there is no out-of-plane stresses. So far, so good? All right. Now, if I take a laminate and I test it, or if I take a single ply, let's continue with a single ply. Let's say I have a single ply with fibers parallel to the loading direction, the top left here. Then I can put a strain gauge on it and measure the Young's modulus. Basically, this plot of stress versus strain would give me, let's call it sigma x and epsilon x, will give me a straight line until it stops being a straight line, but for composites it's almost always a straight line for a single ply. And the slope is the Young's modulus E. So I can measure experimentally the Young's modulus parallel to the fibers from this specimen at the left. Then from the second specimen in the middle, where the fibers now are running horizontally, but I'm loading perpendicular to them, I can measure the so-called transverse modulus, or Young's modulus. And then by doing a shear test, which is not easy, by the way, but by doing a shear test, you get a shear modulus. Also, from this test here, when I apply a tension load in one direction, I can measure with a transverse strain gauge the contraction, or how much it strains perpendicular to the loading, from which I can back calculate my Poisson's ratio. So in general, my Poisson's ratio from this test is minus epsilon 2,2 or epsilon 1,1, or let me use epsilon y over epsilon x. So the transverse strain epsilon y is in this direction, perpendicular to the loading for this specimen. Longitudinal strain is along the load. The ratio of the two, with a minus sign because one of them is compressive, so I can get a positive value, is my Poisson's ratio. Now this is what I can measure experimentally, and it would be nice to know how this relates to the equation that we just wrote at the bottom here, which characterizes a single ply. So there's qxx's, qy's, and so on are given by the relationships given at the bottom of the page here. So notice I have the EL, ET, GLT, and the new LT. Now if you had BLT, it would be bacon, lettuce, and tomatoes. New LT is Poisson's ratio. But I also have the new TL. Now that is the opposite of the new LT, in the sense that Poisson's ratio nu LT means I'm loading in the longitudinal direction, measuring contraction in the transverse direction. If I'm loading in the transverse direction and I'm measuring contraction in the longitudinal direction parallel to the fibers, I will in general have a different Poisson's ratio, nu TL. So in fact, there's another Poisson's ratio there, but that doesn't mean I'm adding another unknown. I still am left with 4. Turns out that, and that's mentioned, I think, in the book among other places. If I open this, we probably don't see. It turns out that nu LT ET equals nu TL EL, which means that the transverse Poisson's ratio, which appears in these equations, is given by known quantities as shown here on the board. And that why that happens or why that is true is related to the fact that your stiffness matrix has to be symmetric for a positive definite material and so on. Okay, now everything we said was with one axis parallel to the fibers. In here we had one axis parallel to the fibers in the coordinate system we were dealing with. Well, if that axis, if our reference axis is not parallel to the fibers, we need to know how to transform stress from one axis system to another. So you've seen that before, I'm sure, and if you haven't, you better review it. Basically, if I know stresses in the coordinate system x, y, and I need to determine them in a coordinate system 1, 2, the transformation is here, which involves just cosines and sines of the angle between the x-axis and the y-axis. And that's the standard transformation for a second-order tensor, covered also in the second-year structures course for those of you, some of you, that were with me on that. So that relates stresses from one coordinate system to another, but we also have the problem of stiffnesses. If I have an isotropic material, because the stiffness is the same in all directions, Young's modulus is the same, I don't need to worry about transforming. If in this system, in this material, I'm sorry, we have stiffnesses that are different, that means that as I move now to another coordinate system, I need a way to tell me how to find the corresponding stiffnesses in the 1, 2 system as a function of the stiffnesses in the XY system. And you will see that all of a sudden the quantity Q16 and Q26 appear, which are non-zero in general. What do I mean by that? I mean that our basic ply was defined at the bottom of this page, which had these two zeros, which would correspond to the Q16 or to the QXS and the Q26 here. That's because one axis is parallel to the fibers and the other perpendicular. If I have a random axis system, then those terms are no longer zero, and in fact are given by the Q16 and Q26 terms shown here. And M and N are a cosine of the angle and sine of the angle. This is a fourth order tensor, the stiffnesses, that's why everything has fourth powers in the trigonometric values of the angle theta. That means, knowing what we just showed as relationships at the bottom of the page, that you can now write in a concise form the stresses in any coordinate system as a function of the strains in that coordinate system, but this now will involve the Q matrix, which will be a non-zero matrix everywhere. There will be, in general, non-zero entries everywhere. Notice, again, in this case now my fibers are at this weird angle x following the x-axis, and I'm calculating stresses in the 1, 2 coordinate system. So we defined a single ply, we defined the stresses and strains and the corresponding stiffnesses that relate stresses and strain in a single ply, whether the axis system is aligned with the fibers or is not. Okay, now we are ready to build up and create a whole laminate and put all these plies together. So what I'm interested in is if I put them all together and I apply a force, let's say a tensile force first, I need to know what is the equivalent stiffness of that structure. So I have a laminate which consists of different layers. Obviously I have less plies here than there, but pay no attention to the man behind the curtain. The whole idea is I apply a tensile load and I need to determine the stiffness of this as a function of the stiffnesses of the individual layers. And this is where strain compatibility comes in. Basically, all I know is that if I grab one end and I pull on it, all of the layers will move an equal amount, whether the stiffness is 10 or the stiffness is 1. They are all forced to move an equal amount. So the amount by which they move divided by their original length gives me the longitudinal strain. And if the amount by which they move is the same for all of them, they all have the same strain. So if they all have the same strain, if I number these 1, 2, 3, and so on, the strain in the ith layer is the same as the strain, the constant strain for any of them. So EA for applied strain. Now the strain in the ith layer is the force in the ith layer divided by the E of the ith layer times A of the ith layer. Because stress divided by force divided by area is stress, divided by Young's modulus gives me the strain. So all these are equal to my total applied force. Let me call it F total for divided by the E of the laminate times the area of the laminate. By the way, the area of the laminate is just this cross-sectional area here because I'm applying the force in this direction applied on this surface. So at the same time, I know that summation of Fi equals F total. All the forces in all the layers have to, by force equivalence, add up to the total force. So on the one hand, I know that the ith force relates to the total force through this relationship, and on the other, I know that the summation of all the forces for each of the plies is equal to the total force. That means I can solve for each of these forces to do an example to make it easier. Let's say I only have 2 plies. Then I know that F1 plus F2 equals the total force. I also know that F1 divided by E1 A1 equals F2 divided by E2 A2 equals F total divided by E of the laminate A of the laminate. So if I take this relationship and substitute for F2 here, I get that F1 plus F2 is F1 E2 A2 over E1 A1. Right, so plus F2 equals F total. So I substitute for F2 from this relationship, F1 times E2 A2 over E1 A1 will give me F2. So I can solve for F1 is F total divided by E1 A1 comes out E1 A1 plus E2 A2, and it's multiplied by E1 A1. So the force on in the case of 2 plies, the force in one ply 1 is just the total force times the EA of that ply, product of E times A divided by the sum of the EAs. So in general, I can generalize this and simply say that if I have I plies, Fi is equal to EI AI divided by the summation across all plies of EI times the total force. So this allows me to find the individual force in each ply. Now, what is my total EA? If I know that F total, let's see, I want to say that epsilon applied is F total over E laminate, A laminate. So if I solve for E laminate, A laminate, I get F total divided by epsilon applied, but epsilon applied is also any strain of the different plies, so which is equal to Fi over Ei Ai. So if I combine these, we can show that there's a relationship that will cancel these, and E laminate A laminate is the summation of Ei Ai. And if you cannot follow the missing steps, you can let me know. But in general, because the strains are the same for each ply, the total or the equivalent E times A, membrane stiffness as it's called, for the entire laminate is the sum of the EAs. But what are the sum of the EAs now? If I replace my E with my QIJs, that because we are using Q because it's the convention for plies, then I can write that the EA for the ply I is the Q, corresponding Q, times A, the corresponding area for the ply I. And if the EA for the laminate is the summation of the EAs, with W the thickness, I can relate or calculate the overall EA as a function of the individual EAs for each ply. Now I know I'm skipping steps here, but if you are having difficulty, let me know and we can cover it again. Now, how good is that? All I said was that the total EA of a laminate is just the sum of the EAs. Well, that's the stepping stone in calculating stresses and strains in a whole laminate. To do that, we need to define the so-called stress resultants. Basically, we need to simplify things a little bit. And instead of stresses, we will use forces per unit width and moments per unit width. This is done by integrating over the laminate thickness. Remember, our laminate is what's shown here on the left, and the coordinate system as shown has the positive forces and moments as shown. So this is the sign convention. If it's not the same as other courses, this is the sign convention. The other courses should be aware of this sign convention. In fact, that's all the composites books use that, so we're using the same one. Basically, we say if I take the sigma x, the stress in the x direction, and I integrate it through the thickness z, I can call that quantity nx, which is a force in that direction. It's force per unit width. We'll see that in just a second. Similarly, if I integrate sigma y, I will get the ny, and if I integrate the tau xy, I will get the nxy, which is the shear force per unit width. And if I then multiply by z and do the same integrals, then you can show that these are actual moments per unit width, mx, my, and mxy, with their orientations, positive and orientations as shown in this picture. So let's look at the case of the uniaxial tension that we were doing here. I have width W and thickness, total thickness H, and I'm applying a force in units of force or a force per unit width Nx. Now the average applied stress, sigma 0, is by definition my applied force F divided by the cross-sectional area W times H. But also by definition the average applied stress is the integral from the bottom to the top as a function of Z, and if the thickness is total H and my origin is in the middle of the laminate, it's the integral from minus H over 2 to H over 2 multiplied by 1 over H to make it into an average. So if I then recognize that this quantity with the integral we just defined at the top here of the page as Nx, I can substitute and arrive at the relationship that says my applied stress, average stress, is this force nx divided by the thickness of the laminate. So if I take my force per unit width and divide by thickness, I arrive at the obvious thing, a stress. It's just that most people don't recognize that this is force per unit width. It's not force per unit thickness or anything else. It's force per unit width, which divided by the total thickness becomes the average stress. So in-plane behavior. In fact, in composites, we will separate the in-plane from the out-of-plane, and then we'll talk about coupling where the two are combined. So in the case where we only have in-plane loads, and we also assume that there is no bending. This means that there is that the layup is symmetric. We will define that later on. Don't worry about what that means. What I need you to keep in mind is we have an applied load which only causes in-plane deformations. So this means that the strains anywhere through the thickness are constant and equal to their values at the mid-plane. And traditionally we put a 0 or a naught to denote the mid-plane strains. So mid-plane strains, epsilon 1, epsilon 2, and gamma 1, 2. Now if I take that relationship from before, which was, 1, 2, 1, 1. I take this, which is the general expression of stress-strain equations. I integrate that with respect to z. So if I take the first one, I had sigma 1, 1 was q11 epsilon x0 plus q12 epsilon y0 plus q16 gamma xy0. So I just integrate everything with respect to z. I know by the definition we just introduced that the left-hand side is my nx, the force per unit width. And then, because I said this is all in plane, and this is a constant strain, epsilon x0, epsilon y0, and gamma xy0 with respect to z, I can take those strains outside the integrals. As soon as I do that, I end up with these interesting quantities, integrals of the stiffnesses through the thickness, integral of stiffness q11, q12, or q16. And these are now called by everybody A11, A12, and A16, which means if I take my stress-strain relationships and I integrate through the thickness, I arrive at my basic plate relationships, which relate the forces per unit width to the strains through this A matrix. I just showed you how A11, A12, and A16 come about. So in general, Aij, where I and j can be 1, 2, or 6, are given by this integral through the thickness. Because within each ply, however, the corresponding Qij is constant. So each ply has its own Qij, Q11 or Q16 or whatever it is. So I can simplify these integrals as summations over all plies. Basically, within each ply, I only get the Qij of the kth ply. And the integral with respect to z would give me a zk minus 1. Basically, this is my z-axis now. And I call this z0. This is z1, z2, and so on. So if I am doing my integral of dz from the bottom layer to the top layer would be, let's say, z2 minus z1 in this case. So in general, it would be the z coordinate of the top layer of the top location of a ply minus the corresponding one for the bottom, and that multiplied by the corresponding Qij. If I take that and add it up across all the plies, I get the corresponding term in the A matrix. And your homework 1 has a lot to do about the A and the D matrix, and you guys will have to either write a program. I strongly recommend to do this, or use the packages that we have available. Are there any questions? I'm done for today. Oh, okay with you? Okay, all right. All right, I will see those of you left on Friday, and we have a bigger room on Friday, but hopefully next week maybe they can give us another room. We'll see what happens. And if anybody has that paper with a sign-up sheet, please, if I can bring it over.